Hi everyone and welcome to episode 5. Now, before we get into what today's episode is going to be all about, I want to address something that I mentioned in episode number 4. At the end, I mentioned that I would be releasing the USB to GPIB source and files and whatnot either that day or the following day. And if anybody's been paying attention, that obviously didn't happen. Now, don't get me wrong, my intention is still, of course, to do so. It's just things changed slightly throughout the week where I had to make a little change here, a little change there. The code technically in its current form hasn't been tested because it's going to use a different oscillator in the release version than in the version that I have sitting around at home to allow for higher baud rates. So what I decided to do is wait until I get the boards and the parts for my first actual release comes into me so that I can actually test it, make sure that everything is actually indeed okay, and then with that, release it to the public. I just figured that it'll allow me to make sure everything's working before actually just throwing it out there and then me hearing from a bunch of people, this isn't going to work, there's a problem there, blah, blah, blah. And I can't actually back up any of my side of the claims or whatnot. So, oh well. But anyways, for today's episode, we're going to be kind of continuing on the same sort of path as we were talking about last time. Last time we were doing some signal processing related stuff, and today we're going to be doing the same thing, but as opposed to last time when we were talking about sampling a signal, we're going to be talking about something that you can do once you already have the signal already all sampled. So we're going to be talking about decimation and interpolation, or also known as downsampling and upsampling a signal. So there's a few manipulations that you need to do to your data to properly be able to perform these steps. So we're going to be talking about it. We're going to be going back to the whiteboard, which I've already got all nice laid out for us here. And let's go over it, shall we? Okay, so first let's start off with decimation or downsampling a signal. So let's say you have some signal that you've sampled it, and you've got some data points or whatnot, what have you, blah blah blah, and these are your values, right? So let's say you've got some signal like this, and what you've done is that when you originally sampled it, you sampled it such that your sampling frequency was equal to 4 times the Nyquist frequency. So instead of sampling at, say, twice the Nyquist frequency, we've done it at 4 times. So we've oversampled the data. So what that results in is, of course, a little graph that looks like this. All right, similar to what we were looking at last time for the frequency domain, right? So do that. Trying to aim both the camera and my marker at the board. So let's say we've got some sort of frequency distribution that looks like this, right? And this is our, right? So this is our continuous frequency domain spectrum, right? So then when you sample that, you end up getting that other graph that we were talking about last time, where then you have your replicas, right? And then you've got your more that way, blah blah blah, where they repeat, right? Let's look over here instead. So if you've got that signal, right? And then now this is going to be our sampled frequency spectrum, right? So you've got your center here, and remember we've sampled at 4 times the Nyquist frequency. So this is going to be pi over 2. This is going to be minus pi over 2. And over here, you've got your replica, right? Where this is 2 pi. And of course, you've got another one over here. And the center here is at minus 2 pi, right? So we went over that last time. We talked about that and how different sampling frequencies and whatnot are important and blah, blah, blah. But today, we're going to be taking a look at this. So here, you can see that our sampled signal contains all the data of the original signal, right? We haven't had to do any filtering. We haven't produced any aliasing, any overlaps of the replicas. So there's no problems there. But we're wasting a lot of bandwidth, right? Like, look, we've included potential frequency components that actually don't exist. They don't exist in the data, so that's not there. But we're just not being very space efficient with our storage space, right? So what we want to do is we want to cut that down. We want to make it so that we're removing that. So what we're going to do is we're going to downsample. We're going to downsample the signal. So what does that involve? Well, what that would involve when using a computer is to remove, say, like every other data point or something like that, right? So let's say we want to downsample by 2. So what we're going to do is we call that m equals 2. And what you do, all right, so I'm just going to write down our original givens here. All right, so what you do is you just look at the graph, right, and you multiply everything down here by m. Or in our case, if we're downsampling by 2, right, m equals 2, we're going to multiply everything. We're going to multiply where these lines end by 2, okay? Technically, you actually multiply everything by 2, including where the replicas are. So this replica would actually move to 4 pi in this case. But what ends up happening is that you end up actually introducing additional replicas. So basically, at the end of the day, what it comes down to is you just multiply where this point right here is, or like this point here and this point here, but you just leave the middle alone, right? For this example. So what this ends up being is we end up getting pi, right? And then this would end up, this was before, minus 2 pi plus pi over 2, but now it's going to be minus 2 pi plus pi. So this is now also minus pi, this point here. So these points are actually the same, right? So we can squish them together. So let's just do that. It's minus pi over 2. And we end up getting the same thing here, right? So that's pi, and then you end up getting the same thing on this side, where this is 2 pi here, right? So what does that mean? Well, if you look at this, right, this here shows that what you've got is the signal that you would have gotten if you had originally just sampled at only 2 times the Nyquist frequency, right? Because, as you can see, they just touch, barring my poor drawing skills here, but the idea is that they just touch and they don't introduce any aliasing, right? So that's the condition there. So what you end up with is you've just divided by 2. So your new sampling effective frequency, so we'll call that prime, is equal to your old sampling frequency divided by 2. All right, so now what happens if you were to introduce aliasing? Because you don't necessarily always have a nice completely oversampled signal like this. Sometimes you do have a signal and you don't care about the higher frequency parts, so you want to not just low pass filter them, but you want to also then compress the amount of data points that you have stored in your digital system, whether it's in actual storage or in memory or whatever, right? So let's take a look at that, shall we? Okay, so for this next example, what we're going to be looking at is we're going to be looking at a downsampling of m equals 2, and our original signal was sampled at 3 times the Nyquist frequency, right? So, if you just intuitively think about it, we're bringing it down to basically an effective sampling of 1.5 times the Nyquist frequency originally, which is less than 2, which could potentially introduce problems in for a general signal. Now, before we get into that, though, I just figured that what I'll do is take the time for those of you at home that do know the math and are interested in where those extra replicas appear, because if you recall, a moment ago I just mentioned that the replicas at 2 pi and minus 2 pi end up also getting their center ends up getting multiplied by m also, and then new ones end up being created to make up for that. Anyways, so for those of you at home that are actually interested, the equation looks like this. 1 over m from I equals 0 to m minus 1. And then we go e to the j omega minus 2 pi minus 2 pi I over m. All right, so sorry about that, but that's the that's the actual equation. So you end up getting additional replicas that are created from that. So for those of you that actually care about that, then there you go. But you can go into the whole derivation of that and whatnot and blah blah blah. But that's not for today. So what you've got this time is you've got a signal that looks like this, right? So if this was our, n, not m, this is n, right? And then, way down here, you've got your sampling frequency, which is going to equal to 3 times omega n, and you've got the minus 1 down over there also. So remember, so again, this is our continuous frequency spectrum, right? So this is going to be our same. We're just going to go with the same kind of general shape there. And so when you sample that, right? So again, you're going to introduce your replicas and whatnot. So here we've got this is going to be at 2 pi over 3 minus 2 pi over 3. And this is and then of course the replicas are at multiples of 2 pi, right? So you have something along those lines. So of course the height's all supposed to be the same, whatever. Anyways, so now that when you take this, when you look at this originally, you go, oh look, no aliasing, right? Beautiful. But that's of course because the original signal was sampled at 3 times, which is, well, 3 is greater than 2. So, but now we want to downsample this by m equals 2. So we're going to do the same thing as before. We're going to multiply everything by 2, right? So we'll redraw our graph there, and now this point here is going to be 4 pi over 3. This is 4 pi over 3 minus, and we'll say that that's 2 pi, which is our center there. This is minus 2 pi. Beautiful. All right, so now though, if you look at this, right, this was at minus 2 pi with a width of, going in both directions of 2 pi over 3. So this point here is going to be minus 2 pi plus 2 pi over 3. Right? Beautiful. So what that means here is that if you were to do the math, when you multiply that by 2, right, it's going to stretch out like that, and we're going to have some aliasing. Right? And that goes off in that direction, that goes off in that direction, and we've got some aliasing there, which is not what we want at that point, right there. Which is not what we want. right? But it is expected because we are now sampling at an improper sampling rate for the original signal. So you never want aliasing, right? This is bad. But if we're downsampling this to begin with, our assumption is that what we are intending to do with this is to remove the higher frequency components. We don't want them, but we don't just want to do a simple filter. Because again, you do the filter, but you still have those physical data points that are still there. We want to get rid of those high frequency components and free up memory. So what, the simple thing to think of is, well then, all we have to do is filter it, put a low pass filter, remove the parts that will introduce aliases, and then do the downsampling, right? And that's basically what you have to do. So all you have to do is first, if you've got your signal, right? And what you do is you put it through a low pass filter with a frequency cutoff equal to pi over m. Remember, not like quote unquote real frequency units, right? These are just like arbitrary frequency units. It's just arbitrary radians per like data point because there is no time once you've sampled it, right? But we went over that last time. And then of course you downsample by m, right? So in this case it was 2, and then you have your output, right? So then you have your new set of data points. So you take it, you low pass filter it. So what that would end up being is that you would take this and you would apply a low pass filter like that, right? So you would cut out that bit and that bit, and of course, there's replicas, of course, for the filter also, so that then it would cut out that bit and whatnot. But we went over that last time. So you get rid of all that, and then you don't have these anymore because it'll look like this, and then infinitesimally close to it, like so. All right, no more aliases, and of course, repeat it all around. So that's how you do downsampling. So now let's talk about upsampling or interpolation. All right, so now what instead we have is, let's say we had a signal, right? So let's say we've got some signal, X event, and we've got some data points or whatever, right? But now what we want to do is we want to upsample the data. So let's assume that you've sampled the signal originally at a sufficient sampling rate for whatever your purposes are, and your sample data contains all the necessary information that you actually care about. So, well, you sampled it at least 2 times the Nyquist frequency, right? So, but let's say for whatever reason, and I'll give you some reasons later, that you want to introduce additional data points in between the current data points, but without actually affecting the signal, without changing any of the frequency components of it. So basically what we want to do is that in order to realize this, what I'm talking about is doing this, right? Is doing this, is that you have your data point, and then you introduce some zeros, and then you have your next data point, you introduce some zeros, and you have your next data point, and some zeros, right? So you're introducing the zeros as a way to interpolate. So all the original data is still there, right? 1, 2, 3, 1, 2, 3. All the original data is still there. But what we've done is we've effectively created these high frequency components, right? Which is not what we want. We wanted, that. So what we've got to do is we've got to smooth that out and whatnot. But let's talk about interpolation now. Instead of from the time domain, let's talk about it from the frequency domain, right? So let's go with these settings right here that I've written down. We're going to interpolate by 3 So we're going to upsample by a factor of 3, and our original signal was sampled at 4 times the Nyquist frequency. So what does that leave us with? So what we've got is we've got a again, same graph as before, right? So this is our Nyquist, right? And then somewhere down here is we've got our sampling, which is going to equal to 4 times our Nyquist. And yeah, so we'll just write that in. Continuous J capital omega. Right? So after we've sampled it, though, again, just as always, that we keep going over, right, is that we've introduced aliases, right? Where this is, wow, that's not very balanced, is it? Oh well. That's omega. Is it 2 pi? Here's pi over 2 minus pi over 2. It's a pretty crappy pi. And this is, there we go. All right, so now what we do is if we were to upsample this, basically what we're, again, effectively doing in the frequency department here is that instead of multiplying each of these numbers by m, we're going to divide them all by L. So just L, again, L is 3, right? Oh, I'm sorry. You know what? For this one, we'll just make it L is 2. That was L is 3. This is going to be L is 2, just so that everything is nice and consistent with the notes I've already written down. So what we do is we change this all to 4, right? So we divide that by 2 and divide that by 2, right? So see, for you to see this a little easier, what we'll do is now we'll kind of zoom out a little bit. Right? So we've got our nice little one there. Right, so that this is at pi over 4. Pi over 4 is at pi. And this one's at 2 pi. This is the one that was originally at 4 pi. Right? But they go on for infinity, so there's an infinity of them that gets shifted over. Don't worry about that. So that's necessary for it to all work, right? That's minus, whoops. And that's minus 2 pi. And also, this is, remember, this is not something that I really touched on very much, but this is 1 over t in amplitude after you sample, right? The amplitude gets shifted around a little bit. But if we look at this now, right? This is our originals, right? So if I change this back to what our originals were, just so that we can keep track down here, is that our original signal had replicas, of course, just like how all signals do, right? They have replicas at 2 pi intervals. There was nothing at pi, right? So any frequency component that's centered around pi or minus pi is high frequency, and anything that's centered around 0 or multiples of 2 pi is low frequency, right? So what do we've got here? Well, okay, so in our original one, it's all low frequency, right? There's nothing at pi. This is, say that's pi, there's nothing there. Nothing there. Here, we've got now something centered around pi and minus pi. So we've introduced high frequency components, just like you'd expect when looking at the data, right? You've got your point, 0, 0, point, 0, 0, or what? Sorry, in this case, we've only gone by one, by 2. So like that, and then, like that, 0, right? You've introduced these high frequency jumps, which is what these components are. So you got to get rid of them. So what are we going to do? Well, again, we've introduced high frequency components, so how do you get rid of them? You put them through a low pass filter. So what we're going to do is basically your steps then become, you take your signal, and this time instead, first you upsample it. You do that first, obviously, because it's not a problem of aliases, right? Because aliases are something like when we were doing decimation or the downsampling part, right? The problem that arose was aliasing, which is a result of the original data. The problem that arises in interpolation is a result of the interpolation process. So you have to first do it to create the thing that you can actually correct, and then we put it through a low pass filter with both a cutoff frequency of pi over L and a gain of L. Okay, so that's important. And then you have your output. Now you need the gain of L because if you actually go through and you do the math and whatnot, you'll find that the amplitudes have shifted. Like, if you think about it, right? If you take your data points, I'm going to draw this yet again. Data point, gap, data point, right? Blah, blah, blah. Is that if you were to take this and you were to low pass filter it, you're not just going to bring these points up. Like, you're not just going to bring this up to here and this up to, say, here or something like that, right? To make it all nice and make it all nice and smooth. You're going to end up actually doing something like this. You're going to end up, see, it's again, I'll just draw this graph again. So let's assume that that's what your data was. You're going to end up bringing this one down, this one down, this one up, and that one down, right? You're gonna end up actually squishing down your original signal. So you need that gain to then lift it back up. So what happens is that, well, if you think about it, if we need a gain of L, it's because this gets brought down to half, this is halved, right? So you'll end up with something that looks like, like that instead. Don't know why I drew that there. There we go. So you'll end up with something like that as opposed to something like that, which is what you kind of more wanted as opposed to the squished signal. So you've got to give it some gain. So now, what was the point of interpolation though? Because all you've done is just created additional data points for you to now store in your computer. So we'll just touch quickly on that, and that should be the end. So the reason why interpolation is going to be something that's important for you to know how to do also, in addition to downsampling, is other than the fact that you might actually come across a legitimate reason why you do indeed need additional data points to then do further work on or what have you. Again, you're not actually creating additional information, you're just using more storage space basically, is because let's say you want to downsample at a non-integer value, right? So let's say you wanted to take your sampling frequency and you wanted to map it to, you wanted to go to a new sampling frequency, right? Where it's equal to alpha times your original, right? Where alpha is some non-integer value. So let's say then that using the letters that we were talking about before, alpha equals to L over M. So as long as you can express the factor with which you wish to adjust your original sampling frequency at can be expressed as a fraction, you can then use a combination of interpolation and decimation to produce your desired result. So how do you combine these all together? Well, if we think about it, right, for interpolation we had to interpolate, then low pass filter, and for decimation we had to low pass filter and then do the actual downsampling part. So if you think about it, well, why don't we just do it in that order, right? So why don't we just take our signal, right, and then we'll interpolate by L, and then put it through a, whoa, that's a bad F. There we go. Put it through a low pass filter with a cutoff of pi over L and a gain of L. And then go through another low pass filter with a cutoff of pi over M. And then go do our downsampling. And then we have our output. I'm sorry, I have no idea if I was just actually pointing at anything when I was writing there. That was fairly bad of me. I'm sorry about that. But yeah, so signal, low pass, filter, signal, interpolate, low pass filter, decimate, resultant signal. Now this part though, this part is just one step. You don't need to do low pass filter twice. So you can actually compress that down into a low pass filter, where the cutoff frequency is equal to the smaller of the two numbers and has a gain of L. All right, so that means the smaller of these two numbers is going to be which one's bigger of L and M, right? Because the bigger the denominator is, the smaller the fraction becomes. So yeah, that's your steps involved in adjusting the sampling post sampled sampling rate of your signal. So then you can go forth and do some stuff. This can be used to do, say, processing on images. You want to do some blurring effects. You can apply low pass filters and whatnot. Let's say you've sampled some audio at a really high sampling rate, and now you want to compress it down to fit on another device, and you don't want to use the codecs already freely available. Well, all you have to do is you just low pass it and decimate it, or if you want to go by some other fraction, right? Well, then just do this order, right? So yeah, that's pretty much it. That's involved with down and up sampling. So I hope you all enjoyed this episode. Now, there's of course a lot more detail that I could have gone into on various of the topics that we discussed today. Could have gone into a discussion about some of the more math, or I could have talked about more about the actual filtering process, or how to convolve your filter with the original signal, and et cetera, et cetera. There's so much that you could talk about. It's I took an entire class on it, right? It was, what was it, 4 months long, and we still barely managed to get through all the material. And even that, it was just an introductory course. There's so much that you can do in this topic. It's pretty cool, to be honest. So, oh well, maybe another time. Next time we'll probably talk about something different. We'll leave the signal processing topic for a later date. But oh well. And talking about my videos too, it seems to be that I've managed to get into a non-intentional pattern of doing these on Saturdays. Oh, it just happens to be the best day that works out for me right now. Right now it's winter here in Canada, so the sun goes down at a fairly early hour, so I can't record videos during the week because I don't have adequate lighting if the sun's not out, and yada yada yada. Oh well, right? It's better than nothing. So I hope you guys enjoyed this again, and I'll see you guys next time. Bye.